Hi, my name is Akshay Desai, and welcome to EKF localization for a turtlebot. This is my ECE470 extra credit assignment, and in the next few minutes, I'll show how an extended Kalman filter, or EKF, fuses real encoder odometry and LiDAR measurements to keep a turtlebot localized with sub-decimeter accuracy. Motivation. Why do we care? Any mobile robot must know where it is to drive safely, plan paths, and avoid obstacles. Wheel odometry is cheap and high rate, but it drifts because of slip and bias. LiDAR range and bearing to fixed beacons give an absolute position, but they're noisy and only arrive about 10 times a second. By fusing these complementary sensors, we get the best of both worlds. Our goal is to demonstrate that fusion with an EKF in simulation, then quantify how much drift it removes. Here's the formal problem. Our state vector is planar, SE2, XY, and heading theta. Controls are the linear speed V and the angular speed omega. We compute from the wheel encoders. The LiDAR gives, for every visible landmark, a range R and a bearing beta relative to the robot. We drop 4 beacons into known global positions: the origin, 2 meters up and to the right, 4 meters down right, and 6 meters straight ahead. Even that sparse set is enough for global correction once at least one beacon is in view. For the prediction step, we use the classic unicycle method model. Over a 0.1 second timestamp, the robot moves the v delta t in whatever direction it's facing and rotates by omega delta t. Because the cosine and sine make the model nonlinear, we linearize around the current estimate. The state Jacobian F captures how small errors in position propagate, and the input Jacobian B injects control noise. We assume Gaussian process noise with 5 centimeter per second translation variance in 200ths of a radian rotational variance. That finishes the predict half of the EKF. When a landmark pops into LiDAR scan, we get 2 numbers: the Euclidean range and the bearing relative to the robot's front. Those come from these nonlinear equations. Again, we linearize, this time with the measurement Jacobian H. We format the innovation by subtracting the predicted measurement, wrap the bearing into minus pi to pi range, and weight it by the common gain K. The gain shrinks the covariance and pulls the mean estimate towards the ground truth. We repeat the update for every landmark seen in the current scan. Putting it all together, each cycle we predict the next pose and its covariance. Then, for each landmark in view, we compute its Jacobian, form the innovation, apply the common gain, and correct both the mean and the covariance. The math is constant time per landmark, so the whole filter easily runs in real time on a Raspberry Pi. We test the filter in NumPy using a 40-second mission. For the first 20 seconds, the robot drives a constant left turn, tracing a circle. For the next 20, it straightens out and drives forward. All the parameters, wheelbase, timestamp, and sensor noise are listed here. The entire demo lives in a single 140-line script called ekfturtlebot.py and uses only NumPy and matplotlib. A fixed random seed makes every run reproducible. Here are the results. Black is the ground truth trajectory. Red dashed is pure dead reckoning. It spirals outwards during the circle and ends up nearly a meter off on the straight segment. Blue is the EKF estimate, so close to black that they're almost indistinguishable. The thin light blue rings are 2 sigma, or 95% covariance ellipses drawn every second. Notice how large they are at the start, then tighten rapidly once landmarks are observed. The 4 green marks mark the beacon locations. Only 2 are inside this view because the robot never drives near the others. Visually, it's clear the filter tracks the true pose and suppresses drift completely. Numbers back up the picture. With dead reckoning alone, the root mean square position error is 0.82 meters, and the heading error is almost 10 degrees. Plug in the EKF, and those drop to 8 centimeters and 1 degree. That's a 10-fold improvement, huge for tasks like docking and tight aisle navigation. To recap, the EKF is fast, conceptually simple, and under linear Gaussian assumptions, probably optimal. Fusing even a handful of cheap landmarks eliminates unbounded odometry drift. The same Python code drops straight into ROS. Just subscribe the encoder and LiDAR topics. For future work, I'd like to tune the noise parameters online, try an unscented or particle filter, and move to full SLAM where the landmarks are unknown. Thanks for watching. I'm happy to present to you guys. Thank you.